Bad School University.
All right, welcome back. Welcome back to Bad School University. I've had a busy week, but I'm excited to sit down and go over dimensional analysis with you guys. So, analyzing dimensions can tell you if what you're doing in a problem makes physical sense, because sometimes you'll get to the end and you look at the units on each side of the equal sign and they don't line up. So you know you made a mistake somewhere, so you're going to go back through and figure out where that is. So it can come in handy for helping you look for problems. Dimensional analysis is also useful for helping you find the units of constants in your problem. Sometimes they're hard to remember. And then it's useful for helping you to convert between different units, like we did in the last video. And it's also useful for deriving formulas in a more advanced form of dimensional analysis that I'm not going to cover in this video. Okay, so here's some generalized examples of the dimensions inside of typically encountered quantities in science. So to start, we need to know that L is length, T is time, and M is mass. There are some others, but like temperature and so on, but I'm not going to go over those. So distance, for example, uses units of length. So it's an L. Velocity is length per time, so L over T. Acceleration is length per time squared. Area is length squared. Volume is length cubed. Force is mass times length divided by time squared. And then pressure is mass divided by length divided by time squared. Let's take a look at a couple equations and see that the dimensions make sense with this analysis. So we'll start with centripetal acceleration, which is A equals V squared over R. So we know that the units of acceleration, the brackets denote that you're looking at the units of that term. So for acceleration, it is length per time squared, so L times T to the minus 2. For velocity, the units is length per time, and in this case it's squared, so we have L squared T to the minus 2. And then R is the radius, which is just going to be length. So now what we can do is rewrite the equation in terms of our dimensions and then see if everything works out. So we have acceleration, Lt to the minus 2 equals V squared, which is L squared T to the minus 2 divided by L. And then you can see that the L's on the right divide out, so you lose the squared, leaving you with Lt to the minus 2 equals Lt to the minus 2, which means that the units make sense, which is no surprise. For the next equation, we'll look at the simple pendulum, which is the period t equals 2 pi times the square root of length over the gravitational constant g. So with this equation, you actually want to square both sides, makes it easier to work with. So you have t squared equals 4 pi squared times L over g. And now the units for t is time, so squared is t squared. Then the units for L is just length, and then g is acceleration, so that's going to be length times t to the minus 2. And now we can just take the equation up here with t squared And then you can ignore 4 pi squared because it's a constant. So you just take t squared, and that's going to equal the dimensions of L over G. So we have L over L t to the minus 2. The L's are going to divide out, so you have t squared equals 1 over t squared. So that just gets flipped over to t squared equals t squared. And no surprise, the units work out. Alright, now we're going to use dimensional analysis to find the units of a constant. And in this case, we'll be looking at the ideal gas law. PV equals nRT. So P is pressure. The units of pressure, mass times L to the minus 1 times T to the minus 2. The units of volume is length cubed. The units of N is just moles. That's Avogadro's number. Or sorry, that's the number of moles in the gas. And then I lied. We're using temperature. The units of temperature is theta. You're just gonna have to deal with that. I know it's not an angle. Who knows where it came from, but that's what it is. So we're gonna look at P times V. The units are ml to the minus 1, t to the minus 2, L cubed. So if we do some quick math, we end up with ml squared t to the minus 2. And we know that the units of PV is in joules, or energy. But that's besides the point. So we're going to look at NT now. The number of moles times the temperature. So that's mole times theta. So when you're looking for the constant, you know that the constant is going to divide out all of the units adjacent to it for the quantities adjacent to it, and then add in the units of what the other side of the equation is. So to find the units of R, you have to divide out the moles and the temperature. So those are going to be in the numerator. So in the constant, they're going to have to be in the denominator. So you know that you have mole times theta in the denominator. And then you need joules, or ml squared t to the minus 2 in the numerator. So that's going to be the units for your R constants. And another way to rewrite this is ml squared t to the minus 2 mole to the minus 1 theta to the minus 1. But I don't know. I'm not a fan of that. I like the top one. Joules per mole per Kelvin. Next example, we'll look at gravitation. The force of gravity between two objects is going to be minus g times the mass of the first object times the mass of the second divided by the distance between them squared, r squared. So the units of force is ml t to the minus 2 units for both masses multiplied is just m squared, and the units for r squared is l squared. So again, we want to divide out the units on the right side of the terms next to g and multiply in the units from the left. So let's look at the right side, m1, m2 over r squared. The units of this quantity is m squared over l squared. So that means, well, let me write it out further, m squared times l to the minus 2. So for the units of g, we're going to want to divide out the mass squared, so you have m squared in the denominator, and then divide out the l to the minus 2, so you need l squared in the numerator. And then you're just going to want to bring in the force terms, so m l t to the minus 2. And technically you could stop here because the units of g is newtons, and then you have meters squared per kilogram squared times newtons. So length squared at the top is meter squared, and then mass squared at the bottom is kilogram squared times newtons, and you're done. For this last example, we have Hooke's law. Force equals minus k times the displacement x. So the units of force, again, is mass times length times t to the minus 2. And the units for displacement, or x, is just going to be length. Therefore, we want k to divide out the units of displacement. So we'll have length on the bottom, and then we need force. So we're going to have m l t to the minus 2 in the numerator. And we can stop there because the units for k is newtons per meter, which we clearly have up top here. Class dismissed.